So let us start the session for electric charges and fields. First, let's talk about charge. Now, when I talk about charge is an intrinsic property. Charge, we can denote it by Q is equal to plus or minus Ne. This states that the charge is quantized. That is, it's always in the form of an integral multiple, where E is 1.6 into 10 power minus 19 coulomb. And charge is always conserved, meaning that the charge can neither be created nor be destroyed. It can be only transferred from one body to another. So that is its second property, that is the conservation of charge. So this is its first property, that is it is always in the form of an integral multiple. Second, it cannot be created or destroyed. Okay, that is the net charge is always isolated. And the third thing is, you can add the charges. Electric charges are additive. If you want the total charge, you can do the algebraic sum of the individual charges. And next is, electric charge is also invariant. That is, it does not depend upon the motion of a charged body. Okay, so this is the third point, that is, we can do algebraic sum of the charges. And the fourth thing is, it is invariant. And next is we are going to get into Coulomb's law. So talking about Coulomb's law, it's an inverse square law. Okay, it states that electric force of attraction or repulsion between any two point charges. Okay, so that is F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. This is Coulomb's law. Okay, where epsilon naught is the permittivity of free space. And what is this k value is 1 by 4 pi epsilon naught. Okay, these are constant. Okay, its actual value is 9 into 10 power 9. Its unit is Newton meter square by Coulomb square. Okay, and what I can do is, we have a dielectric constant. This dielectric constant can also be called as relative permittivity. So that is denoted by K. Okay, K is nothing but it's a dielectric constant where we get relative permittivity. This is, we can use this condition for a free space. Instead of a free space, if we are using a medium, then we have to go with the dielectric constant. Okay, then our formula will change as F is equal to 1 by 4 pi epsilon Q1 Q2 by R square. This epsilon denotes, epsilon is nothing but epsilon into ER. Okay, this is the dielectric constant. Okay, so this is called as relative permittivity. We use this when we are replacing the free space by a medium. Okay, so for air, the dielectric constant is 1. For conductor or a metal, the dielectric constant will be infinity. This is in case of air, and this is in case of a metal or a conductor. And what is the value of epsilon naught? That is 8.85 into 10 power minus 12 Coulomb square per Newton meter square. Okay, this is the value of epsilon, that is the permittivity of free space. Now, how to denote this law in a vector form? Okay, we use vectors. So let's know the denotation for the vectors also. So if we have a position vector from Q1 to Q2, that is, if I have a charge Q1 and Q2, now what is the position vector of Q1 Q2? That is, we take it as R12. This is the position vector. Now what does the position vector actually mean? It is nothing but position of R2 minus R1. See, this is the vector. In terms of vector, we represent it like this. If it was q2 to q1, it would be r21, r1 minus r2. Okay. So how to denote a unit vector? So if you want to denote a unit vector, you need the vector, okay, and by its magnitude. Okay, vector by its magnitude is unit vector. So if I want to denote, say for example, I want to denote the force F12. Okay, so this force I want to denote the force on Q1 due to Q2, that is F1. So if I want to denote this force, first I will write 1 by 4 pi epsilon naught, then Q1 by Q2, then I have to write the corresponding position vector, that is R12 square into its unit vector. What is its unit vector? R12 cap. So this is the vector representation of the law, Coulomb's law. See, this law you can either express it in form of unit vector, and you can also express it in a cubic form. See, simple. The F12 vector, in this for the force, the value was 1 by 4 pi epsilon naught and Q1 by Q2 by R12, okay, the square and into its unit vector, right? This was the thing. Now what I can do is Q1 by Q2 R12 square, I can represent my unit vector by its magnitude. Okay, so here comes 1 by 4 pi epsilon naught. So if I do this, I will get the answer as Q1 by Q2 R12 cube into its vector. So if I want to express this thing as a vector, here the cube will come. If I want to express this thing as a unit vector, here square is coming. This is the difference. Both are vector form of this Coulomb's law. Okay, and you should know that F12 is negative of F21. Okay, next is electric field lines. Electric field lines, like for positive charge, if I have a positive charge, the electric field lines move away. If it's for a negative charge, they come towards the charge. This is how it comes towards the charge. And if it's like we have two positive charge, okay, suppose we take two positive charge, they go away, but there is a repulsion. They go away like this. Okay, they never meet each other. They'll go away like this because we have repulsive charge and they go outward. They are not coming inward. Okay, sorry, outward. They will go outward. Okay, and for negative it will be inwards. See, if I have a minus q and a plus q charge, then this would be like, it will go like this, in from positive to negative. Here it will be inwards, whereas here it will be outwards. Okay, and next is we are going to learn the electric charge distribution. Let's take first linear charge distribution. For linear charge distribution, the Q is nothing but lambda L. Lambda is linear charge distribution. Lambda is Q by L. That is, lambda is for charge upon length. Okay, so if you want the charge, you take it as lambda L. Now for surface charge distribution, what is the case? For surface charge distribution, it is represented by sigma. It is by charge upon area. And for volume it is rho. We denote it as rho. is charge upon volume. Now we're going to talk about the electric field intensity. Electric field intensity is nothing but we are going to denote an electric field. Electric field intensity, the formula is see, this is like the electric field intensity at a point due to a source charge. Okay, that is the force experienced per unit positive test charge placed at that point. Without disturbing that source charge, we can express in this way. Q naught here. Q naught is it is a test charge. It is tending to 0. Okay, it must be very small. The test charge must be very small so that it does not produce any electric field, its own electric field. And the unit for this electric field intensity is Newton per Coulomb. Okay, here we have force Newton and here we have charge Coulomb. Okay, and this is, we have one more formula, that is E is equal to kq by r square, that is k is nothing but 1 by 4 pi epsilon naught. Okay, this is the electric field intensity at due to a point charge. What is the electric field intensity due to a system of charges? You have to just add those corresponding electric field charges. Okay, like this you have to add this electric field. Okay, and what is electric dipole? Electric dipole is nothing but, let's say I have a negative charge and here I have a positive charge. In this condition, at the center there is, let's take the center O. The distance between these two charges is 2a. This distance is a and this distance is a. The electric dipole is denoted by P. Okay, the length is 2a and the charge is q. So we take it as the product of the distance and the charge. The two equal and opposite charges are separated by a small distance. That is the electric dipole. See, the dipole moment is a vector quantity